So today I want to talk about weight and how it could change based on the situation you're in and how to calculate that. Now, before we even get there, I just want to kind of talk about what it is in general. Weight is unfortunately used very, very similar as in mass. They're very different. In physics, mass is the amount of matter something has, while weight is the amount of gravity or force of gravity acts on that matter. Now, like I said, it's unfortunate they're kind of used interchangeably. Outside of physics, somebody can ask me how much do I weigh, and I can respond 150 pounds or let's say 70 kilograms. But when I'm saying that, I'm actually saying a mass. It doesn't really make a difference on Earth, but it does make a difference if we're other places. So on Earth, all of us are going to experience mass the same. So if I'm 100 kilograms, you're 100 kilograms, we're going to experience it the same. Even if you aren't the same amount of kilograms as me, you're going to have the same concept of weight and mass. So if I say it's 2 kilograms, even though it's a mass, you kind of have an idea how much it takes up. Now, it's not really good because you'll notice here's a picture of Earth, Moon, Jupiter, and the Sun. All my masses are the same, but I'm going to feel a different weight based on the planet or star that I'm on, because that's based on the amount of gravity's acting on me. So that's confusing, but let's kind of define them both kind of separately. So mass is defined as, or at least before, it was defined as 1 liter of water. So they just wanted to take up space. Liter made sense because it was based on the metric system, which is kind of funny too, because that's based on Earth, which isn't a constant, which you'll kind of understand in a few minutes. But mass was based on length. But anyway, we get it. Mass is the amount of water, 1 liter of water. Unfortunately, water, it changes based on temperature. So they wanted something a little bit less volatile that will evaporate or change volume based on temperature as well, which is a little bit harder to measure. So then they came up with an artifact, which was called the International Prototype. It was made 90% platinum and 10% iridium, and it was kept in a really safe place. So this was the thing that was made, and all measurements were based on this object. So they'll pass along to different countries. They'll copy the exact mass of it, and then using weight, and then using that as kind of the base of all measurements. So this was pretty much used until 2018. Then they kind of wanted to go away from it. They wanted to make sure that this is true for all situations. Even though it's platinum and iridium, which is really, really stable, it was still losing mass here and there, even if it's protected like that. So now we based our mass on a constant, in this case Planck's constant, and that never changes. Now, do we use Planck constant to kind of calibrate stuff? No, but it's more of just a definition. We still use this entity or some sort of entity to kind of measure mass, or at least base our measurements off of that. Now, what is weight? Whoops. Weight is pretty much what we feel, right? Gravity is always the same. Let's say the mass of the person is 50. And I'm going to do something different before I forget. From now on, we're going to make gravity 10 meters per second squared. And the reason why we want to do that is we're talking about forces. We're not measuring anything super accurate right now in class. So I'm going to make it 10 just to make these problems easier to do in my head. Okay, it's going to give us close enough answers, but it's going to be off because we're using 10. But we could now do things in our heads really, really quickly versus trying to figure out in our calculators. So here we have Fg. Let's say the mass of the person was 50. So Fg is technically mass times acceleration, but you change it into G because that's the gravitational pull. Sometimes they'll show it like this, negative mg, just to show that it's down. I know mentally it's down, so I don't have to put a negative sign, but as good practice you usually do. So m is 50 kilograms times gravity, which is 10 meters per second squared, and you get negative 500 newtons. Okay, this never changes on Earth. It's always the same. No matter what you're doing, jumping up and down, falling, going on an airplane, your force of gravity is always the same. What's going to change is what you feel. And what keeps you from falling to the ground is Fn, force of the surface, right? Gravity wants to pull you down, well, the gravity wants to pull you down, and the ground wants to push you up. And this pushing up is what we feel as weight, right? So if I'm not moving right now, gravity is not going up or down. I'm still, Fn is equal to the absolute value of g. So most of the time, in most situations, it's equal. So it makes sense. My weight is very similar to mfg, so it's the same thing. But that's always true. One place where it's not true is elevators. Okay, so in an elevator, I just have a bunch of pictures of really tall buildings. You have in big buildings, you have elevators that pull you up and down, and they have to speed up and slow down. So here's the situation. Normally you're in an elevator. That's weird. Normally you're in an elevator. And your goal is to eventually get to the floor you want. Usually when you get in the elevator, it's not moving. And then usually when you get off the elevator, it's also not moving. Somewhere in between, it is moving. I'm going to make up a number. 5. Okay. Somehow I have to go from 0 to 5 and then slow down from 5 to 0. Here, I have acceleration. Here, I have acceleration as well. Technically deceleration because you're slowing down. During these times, we're going to feel a different sensation for our weights, and we'll try to explain that. The same thing happens as we're going down. Your initially is going to be 0. Instead of positive, it'll be negative, and then it'll go back to 0 again. In between, since you're changing velocity, you're going to have acceleration, which means you're going to feel a change. Okay? Now, if you're at rest, we want to know what our weight is. Technically, that's Fn. Now, you can have both elevator and person, but when you're talking about Fn, you only care about the person, and I'll try to show that. Does the person know what's happening outside the elevator? And the answer is no. If you didn't know, there's a cable connected to the elevator, and it's actually connected to a pulley, which then is connected to a counter of mass, which is almost the same thing as the elevator. So it's kind of, it should eventually just balance out, and then the motor, all they have to do is move it up or down of balance weights. And if it's balanced, it's pretty easy. The motor right here is not actually moving up the elevator, it's just moving up the imbalance between them. So typically, this weighs exactly the same amount as the elevator empty, so it's actually really easy to move. In class, we'll have pulleys, and then if they're both the same mass, it takes very little effort to change the direction. Okay? Now, even though the person inside, they have no idea what's going on the outside. All they know is the elevator floor is pushing up, and gravity is pulling down. Okay, so that's all the forces acting on the person. It doesn't care what the elevator is doing. So the sum of all forces in the y direction for the person is just Fg plus Fn. In this case, it's at rest, so that means velocity 0, acceleration 0. Remember, sum of all forces is also equal to ma, so that's 0, so Fg is equal to negative Fn, or the opposite. Fn is equal to the negative Fg. So here they're equal and opposite. So if we go back, I believe we got negative 500 newtons. So that means this is positive 500 newtons. And it makes sense because it's at rest. If it's at rest, they have to equal each other. If one's bigger, that means it's going to accelerate towards that bigger number. So if gravity was bigger, it's going to accelerate down. If Fn's bigger, it's going to accelerate up because that's the imbalance of forces right there. Now, how could Fn get bigger? Technically, it's because of the elevator, right? And we'll get to that. All right, so let's say we're speeding up. So remember I said initial velocity here is 0, and our eventual goal is to get to 5 meters per second, and then at the floor we want to get to, we're back to 0 again. So right now we're just focusing on this part of the journey, going from 0 to 5. So let's say the acceleration is positive 5 meters per second squared, right? So what is, remember we want to know what the weight is in these situations, or Fn. So sum of all forces of the person in the y direction is Fg plus Fn equals ma. And this doesn't change. The only thing that's changed is here we're speeding up, so acceleration is positive 5 meters per second squared. So Fg is still the same, negative 500. Now the mass is still 50. Acceleration in this case is positive 5. Plug it all in and move the 500 to the other side. So Fn is equal to 250 newtons plus 500 newtons, which gives me a total of 750 newtons. So this number is bigger than my at rest. So here at the very beginning of my elevator ride, I'm going to feel heavier. And it makes sense. If you remember back to elevator ride, in the very beginning, it feels like you're getting pulled into the elevator. Well, it's because the elevator is pulling up. The tension here is bigger. So it's going to go up. And because of that, you're going to feel a bigger push up from the ground. All right, next. Here the key word is constant. So if it's at rest or constant, B equals whatever, but A is equal to 0. So whenever you have rest or constant, A is equal to 0, well, what does that mean? Well, it means that it's equal to 0. So here, you're going to feel the same, right? Fn is equal to negative Fg. So if Fg is negative 500, Fn is positive 500. So when you're in the middle of your elevator ride, all of a sudden you feel normal again, or the normal weight or the normal amount of pressure that you feel on your feet. At the very end is the fun part. So when you're slowing down, you're going from a velocity of 5 to a velocity of 0. So that means our acceleration, I'm going to make it up, is negative 5 meters per second. So what's going to be here? The forces are still the same. What's different is the balance between these two forces, right? In the previous one, Fn was bigger because you had to be pulled up. In the middle, they were equal, so there was no acceleration. Here, one of them is bigger because we need to slow down. Well, slowing down, acceleration is negative, so Fg is going to be bigger, but we'll find out. Sum of all forces in the y direction, remember I said I use that interchangeably with F net, is equal to Fg plus Fn, which is equal to ma. Now you can plug in everything you know. Fg does not change in these problems. Fn is the one that changes. Mass never changes either. And in this case, I give you acceleration, which is negative 5. So you get Fn equals negative 250 plus 500 newtons. And you're left with 250 newtons. Okay. You weigh, or you feel, less. Okay, and that's what makes the top part of the elevator fun, because when you get there and you time your jump correctly, it feels like you're going to fly out because you have the inertia or momentum of going up, and as the elevator slows down, your inertia wants to keep you going up. Now, if the slowing down is fast enough, you can feel weightless. So something like Guardians of the Galaxy, which is the data we're going to look at, it pulls you up and down, up and down. So at the very top, you actually feel negative thing because it's yanking you down. But sometimes it has that weightless feeling at the very top as well. Magic Mountain used to have a ride called Free Fall, which you feel weightless, but you're still on Earth. So you still experience Fg, but your surroundings going to give you that sense of weightlessness, which we'll get there. In this case, we're pretty close. 250, which is half your weight. If I really wanted to make an elevator ride that's very uncomfortable, then you make this -10, then you'll feel weightless. Now in real life, acceleration never gets that high in elevators because you don't want your people to throw up in there. Weighing half as much and then weighing almost 1.5 is a lot of stress in the body, so it's usually pretty subtle. Usually increase about 5 to 10 pounds. And one of the assignments I used to assign is bring a scale into an elevator, and you can calculate how fast the elevator is going. And we'll do that at the very end. All right, the same thing could be done on the way down. Now, before I move anything, just remember, whenever you see rest or constant, we know that F, G, and Fn is the same. So you already know that. I don't need you to do the math, but just Fg is equal to Fn. One of them has to be negative. Okay, so Fg is -500, Fn is +500. Simple as that. Now, on the way down, the exact opposite. So as you're speeding down, you're going from 0 to -5. So that means your acceleration here, that's -5, sorry. Your acceleration here is -5 meters per second squared. So it's the same thing, but your numbers are going to have different signs to it. So F net, or sum of all forces, is equal to Fg plus Fn. In this case, it is 50 kilograms times the -5. Oops, why do I keep doing that? -5 meters per second squared. So here you have -250. Fg, you have -500. And then you put on the other side, get 250. So as you're going back down, you're going to feel lighter because gravity has to pull down more compared to force normal. You're going to feel the same, or you're going to feel lighter, sorry. Next one, you're going to feel the same because it's constant speed. So remember, when you see rest or constant speed is the same. If you already did most of the work, you don't have to do it again. Now at the bottom, you're going from -5 meters per second to 0. So you're going to have a positive acceleration. So in this case, same thing. Sum of all force in the y is Fg, Fn equals mass times acceleration, -500 plus Fn. This case, you have mass times a +5 meters per second squared, and you get Fn is equal to 750. So in both cases, the bottom you feel heavier. So if you're going down an elevator and at the very end you go, oh, makes you a little bit heavier, and that's the reason why. Based on the mass, you can actually figure out the elevator speed. So it works either way, and it's pretty cool that you can figure this out. All right, so hopefully that made sense. Just remember, weight is how much you feel, and it could change based on your situation, based on your acceleration. So if you have experiencing a positive acceleration, then you're going to feel heavier. If you're experiencing a negative acceleration, you're going to feel lighter. If your acceleration is 0, you're going to feel 0 change. Okay, so we're going to talk about different roller coaster rides, even zero gravity planes, where they kind of manipulate the surroundings to make you feel weightless.